Okay, so let's have a look at question 8, and it's a eccentric loading problem. So there's a typo in the question here, so it's the second moment of area, not interested in the polar. So let's start off by calculating the second moment of area for the shaft. Well, that's straightforward. So I look up your formula sheet, and it's a pi divided by 4 using radiuses. Outer radius, take away the inner radius to the power 4. And let's look at the diameter. So here we're given radiuses. You can just see that. That's 30 from there to there, 20 from there to there. And I got that to be 5.11 times 10 to the minus 7. And that'd be meters to the power 4. So that's 2 marks. Part B, calculate the critical loading value, stating any assumptions. So we're going to be using one fixed end and one free end. So therefore, on my formula sheet, K equals 2. You're going to need to learn these ones, but it's more than likely to be this particular case. So fixed end and a free end to move. K equals 2. K equals 1 when you've got something that's constricted. You can only go up and down. And you've got 2 pins. And that bends. So that's K equals 1. Next one down, you've got one fixed end. You're trying to hold it there. Another roller section constricted. And it's going to have a pin joint here. Like that. And that would be K.7. And then finally, constricted at both ends. And you're going to put the sort of piston, so it's only allowed to go up and down. So we're going to have something come straight out here, something comes straight out here. And it might bend like that. And that would be K equals 0.5. So for our particular case, for the majority of cases, I expect would either be K equals 1, or maybe a K equals 2, sorry, or maybe a K equals 1. So P critical is pi squared E I over K length of the bar squared. And I had pi squared 101 times 10 to the 9 5.11 times 10 to the minus 7 divided by 2 times by length bar 2 meters, and I need to all square that, and then I found that to be 31.836 kilonewtons. Okay. So for part C, that was quite straightforward in comparison to the other question. Part C, calculate the normal stress. So the maximum normal stress, so again go to your formula sheet. The maximum stress is based upon the load being applied divided by its cross-sectional area, and then we are going to modify this because we've got eccentric loading. Now we are probably going to be using calculators in degrees, so you might want to use pi as equivalent to 180 degrees. Yeah. Or change your calculator so it's set to rads when you come to do the cos calc. So way to approach this is to write out the various terms you've got. So you can see that you've got your P, so that's 5,000 newtons. Your A we already calculated. Oh no, we haven't calculated that. So the A is the tube. It's going to be similar to the second moment of area. This time we have pi. So outer radius 30 times 10 to the minus 3 squared. And then take away the inner 20 times 10 to the minus 3 squared. So outer circle radius area, and then inner circle area. And I found a area of 1.5708 times 10 to the minus 3 meters squared. So I've got my P, I've got my A. What about the E? The E is going to be the distance from the eccentric loading. So that's, looking at the diagram, 150 millimeters. What about my C? The C is then going to be the distance from the neutral axis of the bar that we're interested in bending. So that's going to be in the middle to where we are expecting it to bend. And that will be obviously from this distance from here down to here. So the C will be 30 millimeters. The R, the radius of gyration, we'll find from using I, a R squared. In fact, really we want to know what R squared is. So in my notes I worked out what R is and then squared it, which is a bit silly. So take the square root of I over A, and then you get 18.04 times 10 to the minus 3 millimeters. I suppose the only thing why you'd want to do that is then you can compare your R to your C value. We know that that should be probably less than 1 and roughly equivalent to the C. Then we can work out this bit here, the EC divided by R squared. So put all these numbers together and you get a ratio. Again, we've got length divided by length squared. So no units, 13.833. Now let's work out the sec bit. So sec you need to know is 1 over cos. On my calculator, I didn't bother changing to radians. So I typed in 1 over cos, so 90 degrees, and put in those values. So the P is the 5000 and the P critical is 31.8. Okay. So 31,836. And that gives me a value of 1.231. So this then works out when I put in that number there, that your maximum stress is going to be P over A times by, and it works out to be 18.03. So 5,000 over the cross-sectional area of the tube, 1.5708 times 10 to the minus 3. Radio, and that gives me 57.4 megapascals. And the last bit, D, 6 marks for not very much really. Gonna use now, look up on your formula sheet, the maximum deflection is given by this equation. So the E, and I'm going to use sec pi over 2 P over B critical, take away 1. So that becomes E is 150 millimeters. This you've already worked out up here. Take away 1. And you get a maximum deflection of 34.7 times 10 to the minus 3 millimeters. So that was really easy. Okay, so that was question 8. So question 8, quite a bit easier than question 7. And that's the paper done. If there's any mistakes, please highlight them. They're my solutions, they could be wrong.